Hey guys, so today we're going to be looking at section 5.1, quadratic functions. In this section we're basically going to cover the ins and outs of quadratic functions, their graphs, and all of the important properties of their graphs. Luckily, we've been working with quadratic functions for quite a bit of the semester already, so a lot of this will be review, but we're just going to summarize essentially everything that has to do with the quadratic function in this section. So recall that quadratic functions in standard form are written in the form ax squared plus bx plus c. And so to give you an example of a quadratic like that, we would say x squared plus 10x plus 25, for instance. And because these are functions, we're just going to set f of x equal to it, essentially. Now, we've seen quadratics in this form before, and typically how did we solve them? Well, you could solve them by factoring by hand, using either factor by grouping, or by using the quadratic formula, which we really haven't talked too much about, but I'll just write it here briefly. Okay, and so the quadratic formula essentially helps you find the x-intercept of a parabola or a quadratic function. Now, this form, standard form, isn't the most useful to us when it comes to wanting to graph a quadratic function. The form that helps us graph quadratic functions is called vertex form, and vertex form looks like this: f of x equal to a times x minus h squared plus k. And so what is this form? This form is the form that comes about when you take a quadratic function in standard form and you complete the square on it. So if we were to complete the square on this, we would get to something that looks like this. Okay, and x squared plus 10x plus 25 factors into x plus 5 times x plus 5, which would just give us f of x equal to x plus 5 squared. And so this is a perfect square, so it's not going to have a number on the outside or an a in front, but the idea is the same. Since we've already talked about how to complete the square, I won't need to go through this again, but vertex form is essentially the form you get by completing the square. Remember that completing the square and solve by completing the square are different. When we complete the square, we merely want to put it in vertex form. Okay? And so why is vertex form so nice when it comes to graphing a function? It's because vertex form allows us to see essentially a lot of these properties that we're looking for of a quadratic function. So the vertex of a quadratic, once you've put it in vertex form, is easy to see as the opposite of h, as h comma k. And so because our quadratic that we have here, our example, f of x equals x plus 5 squared, we can rewrite this by adding a 0 on the outside because this doesn't change our quadratic at all. And so in our situation, our h, right, because look how in vertex form we have a negative here. We have x minus h squared. And so it's the opposite of the number that we see on the inside, essentially. And so h is actually, in our example, is negative 5, because x minus negative 5 would give us x plus 5. Okay? So it's always opposite of the number you see on the inside. So in our case, it would be negative 5, and then the number outside added to the outside. And in our case, it's 0. So our vertex for our quadratic function would be negative 5 comma 0. Okay, so another property that we're looking for is the axis of symmetry. So I'm going to sketch our parabola really quickly here, or just a parabola in general. And so if I were to draw this parabola, which represents a quadratic function, not the one that we're working with, but every quadratic has a vertical line that runs through it that acts as kind of a mirror, where the left side of the parabola and the right side of the parabola are essentially reflected across this image. So this point, if you went to the other side of this mirrored line, would correlate to this point, right? And you can see that there's this kind of relationship where every point has a mirrored point to it on the other side of this dotted vertical line. And so that is called the axis of symmetry. It's essentially the line that the parabola is symmetrical about. And so the axis of symmetry, recall that vertical lines are always equations written as x equals some number. So if we were to say this line on the graph represented 1, we would represent this axis of symmetry by x equals 1. So every time you have an axis of symmetry, it's going to be x equals some number. And if we were working with our example here, that number is always the first part of the vertex, so the x part of our vertex. So the axis of symmetry is always going to go through the vertex, which is either the bottommost point, or if we had an upside down parabola, the vertex would be the topmost point. So the axis of symmetry would just be x equals -5 for our example. And so we'll sketch this after we come up with all of these values. And so now when we're looking for mins and maxes, right, if we have a regular parabola or a happy face, we have a minimum because the happy face has a lowest point essentially. And so you either have a lowest point on a parabola, or you have a sad face, an upside down parabola, and then that would guarantee you a maximum, a highest point on the parabola. Notice that when you have an upside down parabola, you don't have a lowest point, right? Because there's always a point lower than it. And because these arrows are going down for until infinity, there's always going to be a point that's lower than any point that you choose. And that's why only downward facing parabolas have maximums and upward facing parabolas have minimums. And so when we're talking about min or maxes, the only thing we're asking for is the y value. What's the y value of that point? And the min or max will always correlate to the y value of the vertex. So if we were talking about this parabola, because the number a in front of our parabola is 1, we know that it's a upward facing parabola. And so that tells us that we have a minimum. So what we would do is we'd circle minimum, and then we'd write what our minimum value is, which is just the 0, the value of the vertex. So you can see just by completing the square on our function in standard form and putting it in vertex form, we're able to glean the vertex, the axis of symmetry, and the min or max value of this quadratic function. Okay, so we'll come back to x-intercepts really quickly and y-intercepts. But what is the domain of a quadratic function? Well, notice that since these arrows are kind of tilted to the side, they are going to be going at an angle. And so they're going to touch every single part of our x-axis. So even though our x is going to go to negative infinity and positive infinity, because these lines, these graphs are angled, they're eventually going to continue, obviously not as sharp, but they're going to continue and touch all the values that are on the positive side of the x-axis, and also all the values on the negative side of the x-axis. So the domain for any parabola, whether it's facing up or down, is negative infinity to positive infinity, because there won't be an x that you miss. And likewise, you could write this as all real numbers. However, the range is different, and hopefully this picture kind of makes it a little obvious. You'll notice that since we have the minimum, right, this is the lowest point on our upward facing parabola. And where are the arrows going? Well, they're just going up, and they're going to continue climbing up. And so because these arrows are pointing upward, they're eventually going to get to any y value above, right? And so they're eventually going to shoot and touch positive infinity for y. And likewise, this upside down parabola, since it's pointing down, it's eventually going to reach negative infinity. But going back to our upward facing parabola, what is the range of this upward facing parabola? Well, range is essentially like domain, but we're only talking about the y value. So what is the range of y values? And if we say, for instance, that this y value is -1, that would tell us that the lowest value, the smallest value that our parabola touches is -1, and the biggest value it touches is all the way to infinity. So we could write this, the domain of this parabola that I've drawn here, the domain of this parabola would be -1, and bracket because it actually touches that point, all the way to positive infinity. And so what about our function that we have here, this f of x equals x plus 5 squared plus 0? Well, since we know the vertex of the parabola is at -5, 0, that means the vertex of f of x is actually here at -5, and then y 0, and then it's an upward facing parabola because a is positive. And so just a simple sketch of it looks like this. Okay, and so what is the smallest value that this touches? Well, it touches 0, but notice it doesn't go lower, right? And so the range for our parabola here, f of x, would be 0, and since it's upward facing, it's going to go all the way to positive infinity. And so the domain will always remain the same whether you have an upward or downward facing parabola, but the range may change. And so you have to be a little cautious about where the value starts and where it's going, because if it's an upward facing parabola, it will end up at positive infinity, and if it's a downward facing parabola, it'll start at negative infinity, right? So we just have to be a little cautious about that. Okay, and so once we have our function in vertex form, this is really the form that's going to help us the most. How do we find our x-intercepts? Well, we know if our function is in standard form, we can find our x-intercepts. So if we had it in this form, x squared plus 10x plus 25, we can use the quadratic formula to find our x-intercepts. Likewise, if we have our quadratic function in vertex form, we're able to use the square root method to find our x-intercepts, or as some of you know it, solve by completing the square. So completing the square, we would have f of x as equal to x plus 5 squared plus 0. And so because this is plus 0, we don't really need it. And anytime we're looking for a x-intercept, right, we're looking for x-intercepts, things that cross the x-axis, the value of y will always be 0. And so what we're going to do to find our x-intercepts is set y equal to 0 and solve for x. Okay, so we have x plus 5 squared equals 0. How do we get rid of the squared? By square rooting both sides, right? Square root, square root. What is the value of an x squared? The square root of an x squared? Well, it's the absolute value, x plus 5 equals 0. And now to get rid of the absolute value, we set 1 equal to the positive version, 1 equal to the negative version. But you'll notice since this is 0, there is no positive and negative 0. 0 is just 0. So we end up with x plus 5 equals 0 and x plus 5 equals 0. And we subtract 5 from both sides on both equations. And you could call this positive 0 and negative 0 if you wanted, but it doesn't really change anything. And so you get x equals -5 and x equals -5. And so we have the same x-intercept. We don't have two of them, we just have the same one twice. And so we can put that as our x-intercept. Our x is -5 and our y is 0. Okay? How do we find y-intercepts? Well, if we're on the y-axis, what does that mean? Well, that means we haven't gone to the left or right any. And so for y-intercept, you set x equal to 0 and solve. And so we'll start here again, and I'll put little lines here. So we'll have f of x equals x plus 5 squared. And if we set x equal to 0, what we have is f of x is equal to f of 0 is equal to, can't draw a 0, f of 0 is equal to 0 plus 5 squared. 0 plus 5 is 5, following orders of operations, and 5 squared is 25. So when x is equal to 0, y is equal to 25. And so our y-intercept is 0, 25. And so this becomes essentially this entire table, or this list of properties filled out for our example, f of x equals x squared plus 10x plus 25. So one thing to be aware of is every single quadratic function will have a y-intercept. You're always going to have a y-intercept. But it is possible that you may not have x-intercepts. So why does that make sense? Well, because think about it like this. I'm going to draw 3 different tiny graphs. So we can have a quadratic function, a parabola, that starts below the x-axis, right, and goes through it like this. Okay, and that would give us 1 point, 2 points, 2 unique x-intercepts. But we're also able to have, just like the function y equals x squared, the original parabola, the parent function, where the parabola sits on the x-axis, right? Kind of like our example does here. It sits on the x-axis. So instead of getting 2 unique x-intercepts, you're only going to end up with 1. So this one had 2 intercepts, 2 x-intercepts, right? This one had 1 x-intercept. And so what's the other option? Well, what if your parabola starts above the x-axis and goes up, right? And so in this case, if you're starting above the x-axis and then you're going up, you're never going to have a chance to cross the x-axis. So it is also possible for you to have 0 x-intercepts. Okay, but you'll notice in all of these, here's our y-intercept, here's our y-intercept, and here's our y-intercept. In all of these images, you will always have a y-intercept. And so how do you tell whether you have 2 or 0 solutions, 1 solution, or 2 solutions? Well, the 0 solutions will be easy because you will get a square root of a negative number. So if your solution, when you try to solve for y equal to 0 or f of x equal to 0, if you end up with an imaginary solution, that's essentially telling you you have 0 x-intercepts, because remember, the Cartesian plane doesn't have imaginary numbers on it, so we can't graph them. Likewise, if you're using the quadratic formula, your determinant, your b squared minus 4ac, will be less than 0. And so if b squared minus 4ac is less than 0, you're going to be essentially doing the same thing, taking the square root of a negative number. And so this tells you you have 0 x-intercepts. Okay, so if you get this one, this tells you you have 0 x-intercepts. If b squared minus 4ac is equal to 0, this will tell you that you have 1 x-intercept. And if b squared minus 4ac is greater than 0, this tells you you have 2 x-intercepts. And so the goal of this section is essentially to be able to put any quadratic function, whether I give it to you in vertex form or in standard form, to essentially fill out this list of properties, and then at the very end, graph it. So now that we have all of these properties, let's go ahead and graph our function. So what I'm going to do is I'm going to erase all of this scratch work, and so we can graph the function that we came up with all these properties for. So Okay, so time to sketch our graph. And so what I'm going to do is make every tick mark of mine count for 5. So as a key, each tick is equal to 5. Okay, so that'll just make it so I can graph the y-intercept a little easier. Okay, so the first thing we're going to start with is the vertex. We know the vertex is at -5, and so since each tick mark is going to represent 5 points, I'm going to put my vertex here. That's the bottom of my parabola. My axis of symmetry is also at this point, so what I'm going to do is make my dotted line at the line x equals 5. My min or max is value 0. That's already taken care of by the vertex. I have my only x-intercept also at this vertex, but I have my y-intercept at 0, 25. So that would be at this point because it's 5, 10, 15, 20, and 25. And so we have our x-intercept, or our y-intercept there, excuse me. My domain is -infinity to +infinity, which it will be for all parabolas, all quadratic functions, and my range is 0 to infinity. And so when I graph my function, I'm just going to connect these two dots like so. And because I know this is my axis of symmetry, my picture is going to be reflected equally on the other side as if it were a mirror. And so I'm going to move and put, because you see how that I'm only one tick to the right. If I go one tick to the left, at 25 I should also have another point. So you'll have to excuse my drawing. Let me try to fix it. And so this is a sketch of our function f of x equals x squared plus 10x plus 25. Or if you want to look at it in vertex form, f of x equals 1x plus 5 squared. And so the real gotcha here is that once you complete the square, you will essentially finding the rest of these properties very simple. If you tried to keep your function in standard form, you're going to find your job very difficult. Now, it's not impossible to do, but it does make your life a lot easier if you're able to complete the square. If you want to find the value of the vertex without completing the square, you can use this property that the vertex, if you have your function in standard form, will always be -b over 2a, comma, f of -b over 2a. And so when you use the quadratic formula, you have a, b, and c, right? The values in front of x squared, x, and the constant. And so you're going to take these same letters and apply them here. So in our problem, we have x squared plus 10x plus 25. And so if we were using this method to find the vertex, it would be the opposite of b. And so since b is 10, it would be -10. And then 2 times a. And since a is 1, 2 times 1. And so that's going to give us, if we reduce that, it's going to give us -5. And then f of -b over 2a, we know -b over 2a is -5. So all we'd have to do is plug -5 inside our quadratic, which is going to give us -5 squared plus 10 times -5 plus 25. And so -5 squared is 25, 10 times -5 is -50, and then another 25. And so this is going to give us 25 minus 50 plus 25 is going to give us 0. And so we can tell that our vertex is -5, 0, and you can see that that matches the vertex we got after we put it in vertex form by completing the square. So I hope that was helpful for you guys. This is where I'm going to cut this video, and I'll see you in the next one.